And for 3, 9 alpha, we're going to ask you to go here. I'm going to ask you to go to y equals, now you got to listen to this. And in y1, I have 2 caret x. I want you to type 4 caret x. You're typing 4 caret x in y1, and you're turning on y6. And I have the derivative of y6. You have it in another line. That's what I'm asking. Yeah, you have 4 caret x, and turning on the derivative, whichever line you have that stored in. And I got this picture with 2 caret x, all right, where the parent graph is blue, the derivative is orange. You look up here. Now you compare your picture to what we have up there. What do you notice? You got the same picture we got, even though you have a different thing in y1. Is that right? Yeah, exactly. If you look at this picture, ready? The orange derivative is outside the parent graph. If you look at your picture, the derivative is inside the parent graph. You understand what Adam's saying? So we have different things in y equals. So what would your conclusion be about what's happening between 2 and 4? Exactly. Somewhere between 2 and 4, the derivative is going to map onto the parent group. Because it went in my picture from outside, and your picture was inside. So somewhere between 2 and 4, you would expect there's a number will map what you're looking at. Logical? What's the value of the number? And the number is E. Ready? E is an irrational constant. It's a non-terminating, non-repeating decimal. We've got up here a number line, trying to help you understand that. Between 3 and 4 is the number pi. What is pi? Well, the circumference of a circle is pi times diameter. So if you solve that for pi, divide both sides by diameter, pi is the ratio of the distance around a circle by the distance across it. It's the circumference of a circle divided by the diameter. Between 2 and 3 is another irrational number, that's E, which is in your pre-calc book. But E is the limit of this. As n gets really, really large, of 1 plus 1 over n caret n. So if I look at it this way, you go to the calculator, let's turn this on. You don't need to do this, just look up here. I have 1 plus, in the function mode, of 1 divided by x. Caret x. All right, so I have y6 on the table. So I get an error message at 0, which should make sense to you because you have 1 plus 1 over x, and 1 plus 1 over 0 will give you an error. Look what you have here. So I had 1 plus 1 over 1, that'd be 2, raised to the first, you have a 2. What do you have here? You have 1 plus 1/2. You have 3 halves squared, which is 9/4. What's happening? These values are going up. But from here to here, it went up by 1/4. Here to here, it went up by 12/100. Here to here, it went up by 7/100. They're going up, but it's slowing down. It's slowing down such that the value of this, what's in y2, is the number e that you never stop raising these, what's in the parentheses to an exponent. So I look here and I say, all right, let's go to y equals. You've got e a couple places on your keyboard. And if I type second division sign, second graph, there's the calculator. Now this is the truncated version of e. So that's just what fits in the, that's just what fits in here. And there's e to more decimal points. And you see that as this number goes up, as x goes up, that red value is getting closer and closer to the black one. So we're here. The derivative of e to the x is itself. So if you had this number e raised to the x power, and then you turn on the derivative, the two values would map onto each other. And you will use e as much in calculus as you use pi in geometry. A lot. Now, the derivation is here, except the problem with the derivation, I'm in the middle of the page 172. It's a difference quotient. That's all I need you to see. I'm not really worried about going through all the steps of the derivation. It's the limit as h goes to 0. What's the numerator? X plus h subtract x, which they didn't write out. But it's the chapter 2 difference quotient that looks like this. This will familiar to this piece. What do? You subtract it up. That's what this is. The limit is h goes to 0 if you subtract it up. And the problem is they get to this spot right here, and there's no way to confirm that for you. Where we are, the differentiation for now, they rely on a picture. So it's not really the best derivation, but the derivative of the x in itself. Now, that's not really difficult. What's a little more difficult is what's the derivative of e to the mu? So just like we did using the chain rule, ready? The derivative of e to the x is e to the x times the derivative of the exponent with respect to x, which would be a 1. If you have e to the mu, the derivative would be e to the mu times the derivative of the exponent. So we're looking at example 1. Example 1 says we want to differentiate e to the x plus x squared. So this exponent is your mu. What do? You differentiate it with respect to x. You just use the power rule. You would get 1 plus 2x. So the derivative of the question is itself times the derivative of the exponent. Done. All this is, example 1, is a subset of the derivative of e to the x being itself. So we're going to leave that up there. That's your model. You're going to problem number 9, please. Okay, we look like this. U is the exponent, which is x to the 1/2. The derivative of that would be 1/2 x to the negative 1/2, which is 1/2 times root x in the denominator. That's your derivative. So the question is, what's the derivative of this? Itself divided by 2 root x. Yeah. If you have a fractional exponent in your answer, you would be accurate. You have to think in context of the question. The question had a radical sign in it. You should express your answer with a radical sign. If for a multiple choice exercise, and you did the calculus correct, but didn't rewrite it as a radical, you wouldn't see your choice. Logical? So far what you did was this. E to the x is a subset, the derivative of e to the x is a subset of the derivative of e to the u. Now we have to take that one more step in the general direction and say this. What's the derivative of a to the x? So we don't have a base of e anymore. We want to differentiate this. So the way that the approach to do this is to rewrite a to the x as what? E raised to the ln of a to the x. Why? Because e and ln are inverse functions. They work against each other. So if you raise e, ready to swirl this. E to the ln a to the x is going to be equal to just a to the x. Does that make sense? You have e raised to the ln of a to the x. We're going to set that equal to 10. I want to find out what k equals. We take the natural log of both sides. The natural log of the left this is telling me what exponent do I raise e to give me ln a to the x. That would be ln. Yes, ln k. K equals a to the x. Go over here. And if you write it this way, property of logarithms, you can bring this x out front as a coefficient. Bless you. Now we have this. So I take the derivative of each side. But what is this? This is the derivative on the right of e to the mu. And the derivative is going to be itself times the derivative of the exponent. But ln a is a constant. It's like saying 5x. So that derivative would just be ln a. So the derivative of a to the x is itself times ln a. And the derivative of a to the mu would be itself times ln a times the derivative of the exponent. So this, right here in this box, which I have a summary table at the end of the PDF, is the most general case. See, this is telling you the derivative of a to the mu equals a to the mu, ln a, d mu, respect to x. But if a is e, it's e to the x. you would get e to the x times ln e. The natural log of e is 1 times the derivative of x with respect to x, which would be a 1. The derivative of e to the x is a subset of this. So we're looking at example 2. We want the derivative of this. Y equals 2 caret t take away 3. The derivative, ready, would be 2 to the t, you have a to the mu, ln2, that's on the base, times the derivative of t with respect to t, which would be a 1. You'd have 2 to the t ln2. Subtract 0, because the derivative of 3 would be 0. Now what? When is that equal to 21? This graph, you would have this. This is the input. You wanted the derivative to be 21. That was the question. That's the function. So this order pair is when the function has a derivative of 21. But again, you're building the table, you're building the H chart, so you can make sense of the work that you did. Not just writing answers all over the place. Okay? So we're going to pause the video. That's your model. You're going to problem 29. So you'd have this. It's the same problem, different number. The constant is going to differentiate to 0. So you get the derivative is 3 caret x times ln 3. I want you to set it equal to 5. Does that mean this thing equals 5 when x is the 3 decimal places, 1.379? 3 to this plus 1 would give you that output. That was given. We wanted when the derivative was 5. So this is the summary of what you did. E to the x, the derivative of e to the x itself is a subset of this. This is a subset of that. Well, I got to learn this whole table. No, you don't. If you know this top line, then everything else is a subset of that. You know what the derivative of a to the mu is. Now, the differentiation of this is going to come back up when we do anti-differentiation. You want to go forward this first. You have to undo it in the square. All right? So that is the alpha lesson. The beta lesson is in the derivative of logarithmic function. That is Thursday for everyone.